Hello everyone, in this video we're going to be looking at section 10.5, continuing where we left off in subsection 2. But before we do that, I just want to note I made a mistake. When I did this problem before, this clearly says sine, and I wrote down cosine squared for some reason, and then completed the problem with cosine squared there. So I fixed it now, and I used the power reducing formula for sine, which has a minus sign instead of a plus. So if you were looking at that last video and confused, I fixed a mistake, and in the notes it'll be fixed. So I didn't feel like doing the whole video over again, so you'll just have to bear with me. Okay, so points of intersection of polar graphs. When we normally look at intersection points in the rectangular coordinate system, to find points of intersection, we just set the two graphs, two functions equal to each other and solve. Things get a little bit more interesting in the polar case. And that is because a point may be represented in different ways in the polar coordinates. Remember that anytime I add 2 pi to the angle, that gives me another representation of that point. So a point can have infinitely many different representations. So because of that, we have to be a little bit more careful when determining the points of intersection of two polar graphs. So for example, consider finding the points of intersection on the graph r equals 1 minus 2 cosine theta and r equals to 1. Right? R equals to 1 is just a circle, right? So that's that circle right here. And 1 minus 2 cosine of theta is this shape right there. Right? So as with rectangular equations, first thing we try is to find the points of intersection by setting the two equations equal to each other. Right? So this is r equals, this is r equals. So I can set them equal to each other, and I can get 1 minus 2 cosine of theta equals 1. So if I do that, I end up getting 0 equals 2 cosine of theta, which means 0 equals cosine of theta. And if I solve for theta, that means theta is equal to, when is cosine, pi over 2 and 3 pi over 2. So I get two different points, right? And how do I get a point in the rectangular coordinate system? In the polar coordinate system? Remember, it's radius and theta. So I can plug this radius, I can plug these thetas, just like I can plug x values into either of the y equations. I can plug theta into either of the r equations and get my corresponding radius. In this case, it's obviously easier to look at this constant function to see that the radius is 1 for these 2 points. So I get the point 1 pi over 2 and the point 1 3 pi over 2. Right? Those are my 2 points of intersection that I get from here. If you notice, there are 3 points of intersection though. Right? So which 2 did I find? This would be 1 pi over 2 because there's a radius of 1 and it's the angle pi over 2 with the positive x-axis. Right? So this is the point 1 pi over 2. And then here would be the other point, 1, because as a radius, it's 1 away from the origin, and it has an angle of 3 pi over 2. Right, so this is 3 pi over 2. Right, so we found 2 of the points, but notice we didn't find this other point. Right, we didn't find that guy. So that's why when you're doing these questions, when you're trying to find the intersection, basically what this is saying is we get 2, we should have gotten 3. So what we need to do every time we are solving for points of intersection in polar graphs is to graph it, right? So this is why you should sketch a graph when finding the area of a polar region. You should always sketch it because then you can see if you missed anything and then maybe find those points by inspection, right? So the reason why the third point was not on the graph, it is on the graph. The reason why the third point was not found when we set them equal to each other is that it did not occur with the same coordinates in the two graphs. Right? In other words, they happened at two different theta values and two different radii. So on the graph of r equals to 1, the point occurs. So in other words, on the circle, when does that a point occur? That point occurs with the coordinates 1 and pi. Why? Because if I'm on the circle, right, and I have, this is my point, that angle is pi, and the radius, the distance, is 1, right? So this is the point 1 pi. However, when I'm on the graph of r equals 1 minus 2 cosine of theta, the point occurs with the coordinates -1, 0. Right? So this point is also -1, 0, right? Because 0, remember, is just this angle that is the x-axis. But when I put the -1, that means go in the opposite direction. And so that's why I get that point there. So that is another representation of that same point. And that's because we've got that strange little loop going on in the limacon. Right? So basically, when you're finding these points of intersection, you just have to be really careful that you don't miss any. Right? So in addition to solving equations simultaneously and sketching the graph like we did to find all three of these, note that because the pole can be represented by 0 theta, where theta is any angle, what we should do is you should check separately for the pole when finding points of intersection. So to figure out if the pole is a point of intersection, you should check it separately and don't bank on trying to find it through solving your equations. Okay, so let's look at an example here. We want to find the area of the region common to the two regions bounded by the curves of r equals -6 cosine of theta and r equals 2 minus 2 cosine of theta. Right, so the circle, the big circle that is shifted over, that is the -6 cosine of theta, and r equals 2 minus 2 cosine of theta is the cardioid. Okay, so because we should notice something at first to make our life a little easier. Because both curves are symmetric with what? They're symmetric with respect to the x-axis, right? What we can do, because they're symmetric to the x-axis, we can only pay attention to the part above the x-axis, right? So we can work with the upper half plane and this is shown colored in our figure, right? So what the question really is asking us is to find the area that's common between the two regions, right? So in other words, what the question is asking for is to find this area right here, right? Because that's the area that's common to the circle and the cardioid. However, again, since this shape, which if I outline it like this, it's going to be symmetric to the x-axis, right? So in other words, I can find this area, times it by 2, and I'll get the whole area, right? So that's the goal. And then if you look at the picture that they've drawn here, the colored in part here and here is going to give us the upper half, right? So in other words, we're trying to find the total area that's colored in, or the area of the pink plus the area of the blue. right? So first what we need to do is find the points of intersection, right? In this case, the origin is 1, and this point is 1, and this point is 1, right? So we should find our points of intersection. So when we do that, we set -6 cosine of theta equal to 2 minus 2 cosine of theta. If I subtract 2 cosine of theta, I get -8. No, I'm sorry. If I add 2 cosine of theta, I get -4 cosine of theta equals to 2, which means cosine of theta equals to -1/2. When does cosine of theta equal to -1/2? Well, that happens at 2 pi over 3 and at theta equals to 7 pi over 6. But notice 7 pi over 6, when we think about the unit circle, is all the way down here, right, in the third quadrant. So that is not one that I need for just finding the area of that top half. Right? So this is the one I need, right? And so what is that point? I set theta equals to 2 pi over 3 into any of these, so r equals -6 cosine of 2 pi over 3. Cosine at 2 pi over 3 is -1/2, right? Because that's where it came from, 2 pi over 3. So I end up getting 3. Sorry, this was -1/2. My bad. I'm talking and writing two different things. -1/2. So this ends up being +3. So my point of intersection is going to be the point 3, because the radius is 3, so distance of 3, and at the angle 2 pi over 3. Right? So that's what this point is. I'll just go ahead and box it off in red. That's what this point is right here. This is the point 3 and 2 pi over 3, right? Okay, and the way that the picture is drawn is actually going to be the way that we solve this, right? Because it's going to be easier for us to use the circle to find the area of the blue, and then use the cardioid to find the area of the pink, and then add up the total areas and then multiply by 2, right? So what my claim is that the total area is equal to the area of the blue, which we'll call A1, plus the area of the pink. Oops. Plus the area of the pink, right? Which we'll call A2. So now let's pretend that we just wanted to find this area, right? That blue area. So how are we going to do that? Because let's think about our start and finish, right? I mean, that's the way we do area, right? If I want to find the area of this, remember it's the theta where we start and the theta where we end, and then the radius squared. Right? So if this is where I'm going to start for that one, right? This is the origin here. Notice that I'm going to start here at the radius 0 and theta. This is the line. This vertical line is where I'm starting, right? Which is pi over 2. So I start with the theta that's pi over 2. And then I go to the theta that is 2 pi over 3, right? So to find this area, so I say because the circle has coordinate 0, pi over 2, 0 pi over 2 because it has the origin, which is orange there, is 0 pi over 2 in the case of the blue stuff. Right? This is the point 0 pi over 2 because that's where I start. And then we'll say at the origin, to find the blue area, we integrate the circle from alpha equals to where we're starting pi over 2 to beta equals to, where do we end? Well, beta, we end at 2 pi over 3. Right? So I say, okay, the first area of the blue is 1/2 times the integral from alpha, which is pi over 2, where the theta starts, all the way to 2 pi over 3, where the angle ends, of the circle, which is -6 cosine theta squared d theta. Right? So now we're going to talk about the pink. Right? How do we find the area of the pink? Well, the area of the pink, notice if I wanted to find that, I would start at this angle, which is theta equals 2 pi over 3. And where would I go to? I'd go to here, right? And that angle right here is just pi, right? Again, pi, it's the angle from the positive x-axis, right? So when I look at this here, the region that is in the pink is bounded by theta equals 2 pi over 3, because that's, remember, theta equals 2 pi over 3, that's this line that extends infinitely at that angle of 2 pi over 3, and the other one, which is this theta equals pi, because that's that horizontal line there. So, to find the pink area, what are we going to do? We integrate. Well, remember, the pink area is associated with the cardioid because it's the edge of the cardioid here. We integrate the cardioid from alpha equals to 2 pi over 3 is where we start, to beta equals to pi. Right? So A2 looks like 1/2 the integral from 2 pi over 3 to pi of the cardioid, which is 2 minus 2 cosine theta squared d theta. Right? So the whole area is equal to the blue area plus the pink area which is going to be the 1/2 the integral from pi over 2 to 2 pi over 3 of -6 cosine of theta squared d theta plus 1/2 the integral of from 2 pi over 3 to pi of 2 minus 2 cosine of theta quantity squared d theta. Right? And just to save us a little time, I won't go through these integrals, but this is going to end up being cosine squared, so I'm going to need to use the power reducing formula. And then the other one's going to end up being cosine squared as well, so I'll also have to use the power reducing formula. So here we're going to use the power reducing formula for cosine. We use that a couple of times, and your final area you get is 5 pi over 2. But are we done? Unfortunately, we are not, right? Because remember, that was just, what did we find? We just found the area that's colored in, right? But we needed the total area, which is the area that's colored in plus this, which we knew is symmetric about the x-axis. So in other words, we just need to multiply that by 2. All right? So the total enclosed area is the area we found multiplied by 2. Right? So in other words, 2 times 5 pi over 2, which gives me 5 pi. So 5 pi is the total area, right? Because again, what we found this area, but we wanted all of this, so we just multiply it by 2. Right? So a long example, but a good example. All right, I'll go ahead and finish this video here, and in the next video, we'll talk about the last problem.